Welcome back, guys. In this video, we set up a double integral that gives us the area of a surface over a region R. We're just going to set it up this time rather than evaluate it. Just wanted to give you one more example for your notes. We have f of xy equals x cubed minus 3xy plus y cubed, and we're told that the region R is a triangle with these vertices. This polynomial function in x and y is difficult to sketch, so I'm just going to make my cartoon picture of this. It's not a function that is a well-known function that I can draw. So I'll just write z equals x cubed minus 3xy plus y cubed. This is not what it looks like. Obviously, when x equals 0, we end up with the equation y cubed for z, and when y equals 0, we end up with the equation x cubed for z. So it definitely doesn't look like this. But this is just my cartoon picture. The region R, this I need to specify in order to set up my surface area integral. It's a triangle with these vertices. One vertex is at 0, 0. Another vertex is at x equals 0, y equals 2. And then the third vertex is at x equals 2, y equals 2. So our region of integration is that region right there. It looks like that. So I've got some surface. I want to know, what is the area of the part of the surface that lies above this triangle? So maybe this triangle meets the surface like here. And then on this line, maybe it looks like this. Maybe on this line it looks like that. I don't know. I'm just trying to imagine what that projection might look like on some surface. But that's the idea. We're just trying to find the area of this piece that lies above that triangle. That's not actually what this looks like, but it's a cartoon that helps me visualize what's going on. Okay, so what we always do is we sketch the surface if we can. If we can't, we can just draw the cartoon to get some sense of what's happening. The next thing we need to do is sketch the region R that we're integrating over. Now this time we were very fortunate, it was given to us. So we just plot those 3 points and then we can sketch it, sketch the region. Now the next thing we want to do is set up the surface area integral. So our surface area is the double integral over the region R of the square root of 1 plus the partial of z with respect to x squared plus the partial of z with respect to y squared. Now in order to evaluate this integral, or to set up this integral, I need the partial of z with respect to x and the partial of z with respect to y, and I need a description for R. I need x to go from a function to a function and y to go from a constant to a constant, or the other way around. So I'll do the easy part first. Let's compute the partials. And then we'll substitute into the surface area formula. Okay, so z is given by x cubed minus 3xy plus y cubed. And we want partials with respect to x and y. The derivative of x cubed with respect to x is 3x squared. And the derivative of this piece with respect to x, remember we want to treat this as a constant times x. The derivative of a constant times x is just the constant. And if we're treating y as a constant, the derivative of a constant with respect to x is 0. So this is our partial of z with respect to x. Now we want to do the same thing, but take the partial with respect to y. So we treat x as a constant and we differentiate with respect to y. The derivative of this constant with respect to y is 0. And then over here, I'm thinking of x as a constant again, so this is the derivative of a constant times y. The derivative of a constant times y is just my constant. And then the derivative of y cubed with respect to y just comes from the power rule. That's 3y squared. So we could write it this way, or you could write the 3y squared minus 3x. That would work as well. So we've got the two partials now. Now we'll substitute into our surface area formula. So we've got 3x squared minus 3y and 3y squared minus 3x. So that's one way of doing it. Okay, now what else do we need? We need bounds. We need a way to describe r. We can integrate with respect to x first and then y, or with respect to y first and then x. We've got a couple of options. Let's say that x goes from a function to a function, and y goes from a constant to a constant. Well, we've got to think about what the equation of that line segment is. Isn't that just the line y equals x? Because we're going from 0, 0 to 2, 2. The slope is 1. We go up 2 and over 2. So with that in mind, it's actually pretty easy. X starts over here and ends over here, so we're going from the left to the right. So x goes from 0 to x is a function of y on the side, which is y. Meanwhile, y goes from 0 to 2. That's one way to describe the region. So I could set up my integral this way. I could make this the integral from 0 to y of all of this with respect to x. And then we take the integral of that with respect to y from 0 to 2. That's one version. Or we can go the other way. And integrate with respect to y first and then x. Well, in that case, I need to draw my rectangles this way. And y is going from a function to a function, while x goes from a constant to a constant. Well, in that case, x is going from 0 to 2. And y is going from x to y equals 2. The bottom function to the top function is x to 2. So since y goes from a function to a function, we integrate with respect to y first. X goes from a constant to a constant. Those are on the outside. And the partials are exactly the same as they were in the last step. Now this would be very difficult to evaluate, but we could evaluate it numerically if we wanted to. Either one of these is the right answer for the surface area integral. I guess we could factor out a 3 from this, square it, so we'd have a 9 as a factor there and a 9 as a factor here. We could square these, then sort of collect some like terms and complete some squares. Maybe it would be easy to integrate if we did that, maybe, but maybe not. It would be a lot of work just to find out it doesn't work. But again, I just wanted to go through this process with you. What do? Sketch the surface S. If you can't sketch it, draw a cartoon like I did. Then sketch the region R. That's the region we're integrating over. If they describe it, you sketch it, and then you use your sketch to come up with some description, either where x goes from a function to a function and y goes from a constant to a constant, so our rectangle's oriented this way, or where y goes from a function to a function and x goes from a constant to a constant, so our rectangles are oriented this way. So you sketch R, you describe it, we set up the surface area integral. This requires computing a couple of partials and then using our descriptions of R as bounds. So we did this, and then we substitute the appropriate bounds, or a set of appropriate bounds. For r. And at this point, we would evaluate the integrals if we were asked to, but we were just asked to set these up.